Okay, this is just a brief lecture on the conservation of momentum in the fluid setting. Again, a lot of this will be review if you've had a course in fluid mechanics. We're going to use this to guide ourselves into the Bernoulli equation, which we're going to be working with quite a bit in the course, but I want to see sort of where it comes from. The basic idea is we're looking at conservation of momentum, and this comes from Newton's second law, which you may have used for kinematics and other dynamics courses. Basically, that the rate of change of momentum with respect to time is given by the sum of forces acting on your body, or in this case, the control volume. Here's momentum, mass times velocity. So this is a vector law. There's really three equations here: conservation of momentum in the x direction, the y direction, and z direction. So we have to consider forces, which are also vectors, and they have x, y, and z directions. So that's a pretty critical thing, and it differentiates this from the conservation of mass, which is a scalar law. This is a vector law. Again, we have our control volume, some sort of tagged volume in space. Air is passing through that volume. The volume has a surface with a differential element size of ds. It has inside of it, it's made up of infinitesimally small volumes of size dv. And inside here, the fluid, we have a density and a velocity given by the vector in three coordinates. The edge of this control volume has a normal vector that looks like this, n hat. That's a unit normal, which means it's of length 1. It is direction only. It's a vector which provides only direction. So when we think about control volumes, we're going to work through a problem in the class which has to do with a jet engine, right? And we will consider the control volume basically to be the bounding box of that engine. So such that we only really have fluxes through here, and we can consider a mass flux of gasoline from the tank. The rest of it is solid wall, and we don't have to consider the fluxes there. Of course, a problem like this is greatly simplified because when we think about the flux through this, we can assume that the flow is normal to the face here, and the flow is normal to the face here, and we don't have to consider flow that is coming out at an angle relative to this face, and it's just simple algebra to compute the flux of this face rather than having to do vector calculus to get at the dot product. How much momentum is in these control volumes? Well, we're going to integrate over the whole volume as we did with total mass, but now we're trying to integrate the total momentum. Again, this is a vector law, so this is momentum in the control volume. And we have what about the flux momentum? How much momentum is leaving the control volume? Now think about a jet engine, right? Air is coming in here, air is going out here. Hopefully the momentum leaving out the back is greater than that leaving out the front. That's essentially where we get thrust from. There's a pressure component too, but it's small. So we want that large momentum component, and so we need to know something about these momentum fluxes. How much is leaving this control volume? It's the integral over the surface of the control volume, rho v times our flux again. And we just had rho in the mass equation. Now we're considering, what are we fluxing? We're fluxing momentum. What is the amount of flux? It's the velocity dotted with the unit normal. Again, the convention of the unit normal is outward. So this is an outward flux. That's just convention. You just have to be cautious about it. Outward flux. So this is flux, and we have momentum. So if we consider the full equations now, we have rate of change plus the flux, or contributions coming in or out, has to equal the sum of forces. Oops, it's supposed to be a summation sign. Sum of forces acting on the control volume. We're going to look a little bit more at these forces in a second, but let me just rewrite this so we have it. The rate of change, again, the partial derivative with respect to time of the momentum in the control volume, rho v dv, plus the fluxes through the edge, rho v times the flux of that, and ds, integrating over the control volume, equals the sum of forces acting on the control volume. Just taking an aside here, here's our simple rocket engine again. What's the momentum flux out the back of this rocket? Here's the flux term, right? But if we consider this just a double integral over this surface, but if the properties are not considered to vary along there, this double integral, we can pull everything out of there, and we just simply have rho times the axial velocity u times the axial velocity u times s, which is the area of the exit of this engine, rho u squared s. That's the flux of momentum through this. So this integral turns into this if we assume the properties are don't vary over the exit, and that they're already moving normal to that exit of that control volume. You don't have to worry about this dot product. You don't have to worry about this integral. So in most cases, we're going to use a lot of these kind of simplifications. This is the general form. Now, what do these fluid forces look like? There's a couple different types. There are surface forces. These act on the surface of the control volume again. So we have our general control volume, or we have our engine, or we have a house, or we have an airplane. We have forces acting on the surface of that control volume. There's two kinds of those. There's pressure, and there is a viscous force, or a shearing force. We're going to focus on pressure for a few weeks, and we'll come back to this idea of a viscous force when we talk about boundary layers in several weeks. Pressure forces always act normal to the control volume. If we want to make the surface of the wing an example, the pressure force always acts exactly normal to that wing. It may be positive or maybe negative, maybe sucking the wing or pushing down on the wing, but it's always acting normal to that. It's up to you to convert that force into the components. For example, if this is an airfoil and this is the free stream flow direction, then by definition this is lift and this is drag. So it would be up to you to transfer these forces into these two principal vector directions for force. Again, pressure acts normal to the surface. The viscous force, the strong ones at least, act tangential to the surface. So we'll talk later about boundary layers. Here, let's zoom in on this wing. As the flow goes past it, a boundary layer will be set up. It will look something like this. Flow going past it will be zero velocity at the surface of the wing, free stream velocity somewhere away from the wing, and this and the turbulent eddy viscosity will set up a kind of shear where the action of the flow over the wing will tend to try to drag the wing in this direction. There's a drag force associated with that, and that's a viscous drag force. It acts on the surface of the wing or surface of your control volume, in this case tangential to that control volume. There is a viscous normal force, but it's usually rather weak, and we won't be talking about that in this class. But it has to do with shear present in the flow. Luckily for us, we will consider most flows to be inviscid. Inviscid implies that the viscous forces are not important. The inertial forces, the weight, the mass of the fluid are much stronger than the forces of viscosity. The flow field, typically this is true in the entire flow field except in the boundary layer. So when we will consider our wings, it'll basically be inviscid everywhere around that wing except for in a tiny, teeny layer, I already drew it too thick, next to the wing. That's where the viscous forces are confined. Everywhere else will be inviscid. So that's an important assumption or important truth. So these surface forces, you have pressure and viscous forces. They act on the surface. You also have volume force. So again, here's our control volume. At some instant of time, here's all the air molecules in there. What force acts on all those molecules simultaneously? Gravity. Gravity acts on everybody at the same time. Gravity is a volume force. The only other good example of volume force is electromagnetic force. For example, if you have an electromagnetic drive, fluid is going here, fluid with salts in it, you can set up an electromagnetic field which will actually accelerate this current. That field is acting on every single molecule in the same time. We obviously won't be talking about that in this class, but that's just another example of a body force, a volume, or sometimes called a body force. Now, I won't go through the process of deriving the full set of momentum equations. These are known as the Navier-Stokes equations. I'll write them here. There's one sign I may get wrong, but I will try to write it here. Rho times the acceleration, v dot del, v, that's your nonlinear term, and then so basically you have your acceleration. I'm writing this in differential form. You have your acceleration, you have your flux term, also known as the nonlinear term, and now you have all your forces on the right hand side. You have your pressure gradient force, you have your gravity force. I'm going to put the k vertical direction unit vector there because it only acts in the vertical, only acts in the W momentum equation. You have your viscous force, grad squared u, and if you have, or this is your coefficient of viscosity, and if it's a compressible fluid, you have another term here, minus, I think it's 2/3, do not quote me on that, mu del times del dot u. Okay, so this is a gradient operator here. Here, this is a divergence of the fluid, and as we discussed before, for an incompressible fluid, this term is 0, so this whole term only shows up for a compressible fluid. This is the full momentum equations for the Navier, as known as the Navier-Stokes equations, written in continuous form or differential form, and you can see that they're quite a mess. Now, when you go to ComSol and you solve a compressible flow solution, these are the equations being solved. Essentially, there's three equations here, one for x, or the u velocity, one for y, or the v velocity, one for z, or the w velocity. So as I wrote it here in vector form, there's actually three equations, and then you have equations of state and energy equations and other equations, but they're getting solved by ComSol, and it's a mess. It's a nonlinear partial differential equation, highly coupled, and lots of different scales. The good news is for most of the flow field, we can make some pretty drastic assumptions. If we make the following assumptions: 1, we're working along a streamline, meaning we're tracing the path of a fluid parcel, working along a streamline. And number 2, flow is inviscid. Again, we looked at this before. This is fine, except in the boundary layer. In the boundary layer, we're going to have to do something different. But for the large part, the flow field and the resulting pressure gradient that sets up on account of that flow field, we can assume it to be inviscid. And finally, steady flow. The flow field is steady. So as I mentioned before, we're only considering static situations in this class. So if we have a wing, it's flying, the air is coming at it, and we're looking at the velocity with our little probe right here as a function of time. Sorry, 1 second, this doesn't seem to be updating.